Sample problem 1, heat exchanger. Given with a problem. A hot oil is to be cooled in a double tube counterflow heat exchanger. So the inner tube have a diameter of 2 cm with negligible thickness. The inner diameter of the outer tube shell is 3 cm. The water flows through the tube at a rate of 0.5 kg per second and the oil through the shell at a rate of 0.8 kg per second. Taking the average temperatures of the water and the oil to be 45 degrees Celsius and 80 degrees Celsius, respectively, determine the overall heat transfer coefficient of this heat exchanger. So we are to determine the overall heat transfer coefficient. So the first thing that we should do is to establish our assumptions. So for this problem, our assumptions are the thermal resistance of the inner tube is negligible, such that we will not consider conduction because this is a tube with negligible thickness. Both the oil and the water flow are fully developed. So properties of oil and water are constant. So for the properties of water at 45 degrees Celsius at table A9, so at 45 degrees Celsius, table A9, so we will get the density, Reynolds number, our thermal conductivity, and our viscosity. And for the properties of oil, we will evaluate at 80 degrees Celsius A13. These are the properties. So the table is table A13 and table A9. So we have saturated water and then we have engine oil for oil. So the third step is to identify the working equation. So it is important for us to know what is the working equation so that it will be easy for us to get the unknowns. So for this problem, since we will look for the overall heat transfer coefficient, so we can use this formula for U. So 1 over U is equals to 1 over HI plus 1 over HO. So HI and HO are the convection heat transfer coefficients inside and outside the tube respectively. And we will determine this using force convection's relationship that we can find in week number 2 module. So first is we determine HI. So our unknowns are HI and HO. So first, so this is our schematic diagram. So we have cold water flowing inside the tube that is 2 cm and then hot oil flowing outside that in an annular space that is 3 cm in diameter. So the mass flow rates of oil and the mass flow rate of cold water is known. So the purpose of this heat exchanger is to cool the hot oil. So it is expected that the temperature of the oil will decrease while the temperature of the water will increase during the heat transfer process. So for H, so from the usselt number relationship, our HI can be solved using K over the hydraulic diameter times the usselt number. So looking at this equation, we need to solve for the usselt number and then the hydraulic diameter because we already have K for water in the properties. So in solving for the proper usselt number relationship, we need to determine first the type of flow using the Reynolds number. So using the Reynolds number equation, so that is equals to this, wherein our DH is the hydraulic diameter. So for the inside tube, so since this is a tube, our hydraulic diameter is just equals to its diameter. That's why it is 0.02 meter. So substituting and taking note also that for the velocity, we are not given with the velocity of the water, so we need to solve that using the relationship mass flow rate over density times area of the cross section. So the mass flow rate of water is given, the density of water is already known from the table, and then the cross-sectional area of this tube is pi over 4 d squared. So we can determine the velocity of the flow of the water as 1.607 meter per second. So finally, substituting the value for the velocity, hydraulic diameter, and the viscosity, we can solve for the Reynolds number. So the Reynolds number is greater than 4,000. So for external force convection, or for force convection, so if it is greater than 4,000, so the flow is turbulent. So our relationship should be based on this type of flow. The Reynolds number is greater than 10,000, and then the purpose of this is for the cool water to be heated as it undergo heat exchange with the hot oil. So for the water, we will use this relationship for the Nusselt number for fully developed turbulent flow in smooth tubes. So the Nusselt number is given in this relationship. So we need to identify whether n is 0.4 or 0.3. So for this process, the water will increase its temperature. So that's why we will use 0.4. So we will use this relationship. So Nusselt number is equals to 0.023 Re to the power of 0.8 Pr to the power of 0.4. So we got this from internal force convection for fully developed turbulent flow, wherein water undergoes heating, so N is 0.4. So substituting the values of the Reynolds number and the Prandtl number for water, that's why we have the Nusselt number as 240.247. Finally, substitute the value to our working equation for HI. So we can get HI as 7,651.871 watt per meter squared Kelvin. So to determine HO for oil, so we will determine the convection heat transfer coefficient with oil as our working fluid. So we will use this working equation. So we will determine the Nusselt number for this annular flows. As you can see, the hot oil will flow in the annular space. Since this one is, so the cross section here is for the cold water, so the remaining area is an annular space. So for the Reynolds number, our hydraulic diameter will not be equals to the diameter 3 cm, but the annular space. So the hydraulic diameter for the annular space. So for the annular space, the hydraulic diameter, it can be computed using this formula: D outside minus D inside. So that's why our hydraulic diameter for this annular space is 0.01 meter. So substituting to solve for the value of the velocity of oil, so mass flow rate of oil divided by density of oil times cross-sectional area, which is the cross-sectional area of the annular space. That's why it is pi over 4 d outside squared minus d inside squared. So substituting to our working equation for the velocity, that's why we have velocity of oil as 2.391 meter per second. So to determine the type of flow, so we need to solve for the Reynolds number. So the Reynolds number given us this equation. So we already have velocity, the hydraulic diameter, which is 0.01 meter, and then the viscosity. So our Reynolds number is 630.221. So the Reynolds number is less than 4,000, so the flow is laminar. So to determine the Nusselt number, so we will use for annular flow, we will use the table, this table here, to solve for the Nusselt number. So our table will require us to get first the ratio of the inside diameter to the outside diameter. So that is 0.02 divided by 0.03, so that is 0.667. So as you can see in the table, we only have 0.5 and 1.0, so that's why we need to interpolate between these two values. So interpolating between these two values and solving for the Nusselt number, so the Nusselt number is 5.45. So substitute to our working equation for HO, so that is why we have 75.21 watt per meter squared Kelvin. And finally, we can substitute all the value that we already, the unknowns that we already have to solve for the overall heat transfer coefficient. So that is 74.48 watts per meter squared Kelvin.